Temporal graphs occur in the real world, be it interactions between users on social networks, user-to-item interactions on e-commerce platforms, or even protein-protein interactions or neural activations over time. Temporal or dynamic networks are a uniform, powerful, and a super scalable way of modeling these time-evolving networks and relationships for various different tasks like node classification in a temporal manner, link prediction, and graph classification, and so on. I am Srijan Kumar, an assistant professor at Georgia Tech, and my goal in the next 20 minutes is to share with you my group's work on how to efficiently learn from these time-evolving networks by creating state-of-the-art temporal GNNs and studying their robustness and reliability with various different use cases. First, I'll present a fundamental model that we have created called JODIE to model continuous time-evolving dynamic networks. Next, I'll share a recent model that we have created to learn and make predictions on dynamic and signed networks. And finally, I'll share two studies on robustness and reliability of these temporal GNNs, one in the case of recommender systems, and second for a general discrete time graph model. Let's start with temporal interaction network models. Temporal interaction networks are an incredibly powerful and a very flexible way to represent time-evolving relationships between nodes in a network. Here, I'm taking an e-commerce example where we have a bipartite network containing user nodes and item nodes. When a user node interacts with an item node, a directed edge is created from the user to the item. This edge is associated with additional feature vectors like the timestamp or the amount that the user paid for the item. As time progresses, more user nodes, more item nodes, and interaction edges are created over time. Representation learning presents a streamlined approach to model these temporally evolving networks and represent these dynamic evolutions of users and items, where each user and item can be embedded in a Euclidean space and their evolution can be modeled by embedding trajectories in this space. These trajectories can then be trained for downstream tasks, various different downstream tasks. Our model that converts these temporal interaction networks into dynamic embedding trajectories is called JODIE. This model was developed when I did my postdoc at Stanford with Professor Yuri Leskovich, and this work was presented at KDD. JODIE is a mutually recursive RNN framework that learns to predict dynamic embedding trajectories of users and embeddings from their interactions. It has two major components. The first one is an update component that updates the embedding of nodes after the interaction, and a project component that learns to forecast these embeddings into the future. Let me give very brief details about the update as well as the project component, starting with the update component first. In the update component, JODIE trains two recurrent neural networks, one to model users and another to model items. The user RNN updates the user embedding after an interaction, and similarly, the item RNN updates the items embedding. The user RNN uses the item embedding and the feature vector as inputs to update the user embedding from UT-, which was the previous embedding, to UT. And similarly, the item RNN uses the user embedding as input to update the item's embedding from the previous to the next. As these interactions happen, the embeddings of both the user and the items are updated. The update function, which is shown below, uses the time elapsed since the previous interaction of the same user and the same item in their respective scenarios. Also, you'll note that all the users share the same RNN parameters and all the items share the same item RNN parameters. Next, JODIE then trains a very important projection component or a projection operator that learns to accurately project or forecast these embeddings into the future. Intuitively, these embeddings of users can change very slightly if very little time has elapsed since the user's previous interaction with any item, while the embeddings can change drastically after a long time has elapsed. To model this, JODIE trains a temporal attention layer to forecast these embeddings into the future, which is shown on the left. The entire model is trained to accurately predict future interactions, along with a supervised loss component that can predict based on node labels if they are present. Link predictions can be made on top of this by adding a linear layer to predict which exact item the user is going to interact with before the interaction has happened. We curated 2 new data sets, one from Reddit and one from Wikipedia, with several hundreds of thousands of interactions, as well as ground truth of which accounts or which nodes, user nodes, are malicious. JODIE outperforms existing methods by over 12% in predicting bad users. If you are interested, the code and the data are available at the project link. A year later, Facebook released the TIES model, which stands for Temporal Interaction Embeddings, which has a similar idea of using dynamics of users and item interactions for platform integrity tasks. The TIES model is currently being used at Facebook to detect various different types of fraud, like ad payment fraud, detecting fake accounts, and even misinformation content. This shows the huge potential that dynamic or temporal graph networks have in scaling these models to super large platforms for various different critical tasks like platform integrity. A similar model is also temporal graph networks, which many of you may already be familiar with. It's a great model which generalizes various different dynamic graph models, including JODIE. The architecture is shown here, and it models in a different way, and it's also used on Twitter. Essentially, just another instance of how important and how useful temporal graph-based models are. Next, let me share with you some of the work that we have done very recently on modeling evolving signed networks. In signed networks, edges have a positive or negative relationship, which indicates conflicting relations, such as where positive relations can indicate trust, liking, supporting, or agreement, while negative relations can indicate distrust, dislike, or disagreement. Signed networks have been shown to be incredibly useful in various different tasks, like predicting veracity of posts on social media, detecting polarization, predicting toxicity in conversations, and even conflicts between online communities. Modeling signed networks is significantly different than modeling unsigned networks because these models have to model both dynamics as well as signs simultaneously. And this presents 3 different challenges. The first one is that the models have to follow the rules of balance theory. Balance theory in signed networks dictates that edges are formed to create what are called balanced triads, where each balanced triad has an even number of negative edges. These edges are formed for rules like friend of a friend is a friend and enemy of an enemy is a friend. Balance theory also dictates that unbalanced triads are not favored and are not present in signed networks. Now, these rules are not inherently included already on regular unsigned dynamic network models. Therefore, there's a need to create signed network models. Second, the graph is simultaneously dynamic as well. So we still need models that are able to manage the dynamics as well as the signs simultaneously. And third, unlike JODIE, this model needs to prevent staleness, which means that even if a node does not have a direct interaction, its embedding can still be updated. Existing methods either model sign or dynamics, but not together. The prediction task in this setting is that given a sequence of signed dynamic graph snapshots, predict the sign of edges in a future snapshot. We create a model that we call SEMBA, which does a novel balanced aggregation. Here, instead of each node having one embedding, SEMBA models each node to have 2 signed memories, one positive and one negative. When 2 nodes interact with a positive edge, memories of the same polarity influence each other, which means the positive memories influence each other and are used to update each other, and negative memories update each other. However, when 2 nodes interact with a negative edge, the memories of opposite polarity influence each other. That's shown on the right. SEMBA is built on the TGN, or the Temporal Graph Network Model framework, and it has 4 major steps. When a new edge is created between two nodes, the signed messages are passed between the nodes following balance theory. That's the first step. Next, all messages are aggregated from all the neighbors of a node. Third, node memories are updated by following the balance theory rules, which are then used to update node embeddings in the fourth step. We used SEMBA on multiple datasets, and on average, SEMBA outperforms 4% better than existing models, and up to 50% reduction in negative link prediction false positive rate. Now this is important because existing models are super accurate in predicting positive edges, but with SEMBA, you can not only model the positive edges better, but also reduce errors in predicting negative edges, which is where the strength of SEMBA lies. So SEMBA is the only model, as I said, that simultaneously models both dynamics and sign, and it can be used to simulate and model various different aspects like network polarization on social networks. Next, let me spend a few minutes describing some of the work that we have done on the robustness of dynamic network models. I'll present 2 use cases or 2 case studies. One where dynamic graph models like JODIE are used for recommendation tasks, and next and after that I'll present the work that we have presented today at the TGL workshop by my student Karthik, and I'll very briefly describe that as well for those of you who missed it. So first, let's start with the robustness of graph-based recommender systems. So as we know, these dynamic graph models can be used for recommendation tasks, and models such as JODIE are quite efficient in that. However, in this work, which was published earlier this year at CIKM, we wanted to understand what is the impact of minimal insignificant perturbations that are present in training data, and how they impact the downstream recommendations that are generated for users, such as in an e-commerce setting. Consider how recommendation systems are trained. Historical click data is translated into this dynamic bipartite graph, where a click represents these temporal interactions between users and items. And these clicks can be views, purchases, add to cart, and so on. I'm taking an e-commerce example, but the same thing can translate to friend recommendations and other tasks of recommendations. After this graph is taken and modeled, and after training is done, the trained model is used to generate ranked recommendation list for each user. And this recommendation list is what the model thinks is the list of items in a descending order with the probability that the user will interact with them. Now, users can be quite fickle, which means the interactions that are present in the training data can be quite noisy. And these interactions can be randomly present or can be adversarially present. We wish to investigate whether insignificant minor interaction perturbations in the training data can lead to drastic changes in the rank lists. Obviously, we also need to create a model that generates stable recommendations even in the presence of these perturbations. So we study two different research questions. First, we investigate how stable are these recommendations that are generated by temporal graph models. And second, is that impact uniform across all different types of users? Let's consider this scenario where recommendation systems are trained, and let me explain visually what we mean by these interactions and interaction perturbations. So let's represent these interactions by a sequence where each user is represented as a sequence of interactions that it has made. What is the impact? This is the main question that we want to answer. And what is the impact of minor input perturbations like deletion of an edge or an interaction, addition of random interactions or replacement of an interaction with the other. For instance, in the figure, if we delete one interaction that's in the training data and retrain the recommendation model, which is based on this graph, what happens to the recommendation results? Well, if the model is good and there's one training interaction among millions of training interactions, then deletion of this one minor perturbation should not impact the recommendations. That's what we would hope for. So to model that, we compare rank lists of the users before perturbation and after perturbation and see how much they have changed. If the resulting rank list for items has changed a lot, that means that the recommendations are not stable, and correspondingly, the model that is used is also not stable. To measure this stability, we define a metric of sensitivity for recommendation systems, which measures on average how much does the recommendation change across all users in the entire recommendation rank list after a perturbation is applied. And the sensitivity of recommendation systems is super important, especially for high-stake applications like in medical, finance, or educational domains. For instance, if drug recommendations to one user can be changed by minor noise in even another patient's records, then that can be quite dangerous. Through extensive experimentation, we show that both graph as well as non-graph based recommendation systems are quite sensitive even to minimal random interaction perturbations. Perturbations can alter top 10 recommendation lists by as high as 80%. Alarmingly, one altered interaction of one user drastically changes the recommendation of all the users. Let's look at the plot. So this is a plot that highlights how stable a recommendation engine is, be it graph or non-graph, based on random interaction perturbation of one interaction. If the model is completely stable, then this metric would give a score of 1, while a lower stability will give a score of less than 1. What we see is that, first of all, none of the models have the perfect stability. And the stability of models varies between 0.76 and 0.93, which essentially means that recommendation systems and even graph-based recommendation systems are super fickle to even random minor perturbations. This is of super high concern. To find what's the worst case scenario, we created a new algorithm called Casper that creates a DAG out of these interactions and leverages these interdependencies between interactions to identify the specific perturbation that can be made that will lead to the most change or drop in the sensitivity metric. Next, we compare what is the impact of these interactions across user groups. And importantly and alarmingly, we find that instability has a disproportionate impact on users for which the model is already less accurate compared to those for which compared to the users for which the model is already has a higher performance. This highlights a fairness issue that needs to be addressed. To overcome this instability in these models, we have created a model called 2PAT, which is a adversarial fine-tuning method which is currently under review. With 2PAT, we are able to create recommendation models, both graph-based and non-graph-based, that make the models more stable. Finally, let me very briefly share with you our work that Karthik presented earlier today. I won't go into too many details, but very briefly, let me describe a different setting. So in the previous work that I just presented, we're looking at an untargeted setting of when dynamic graph models are used for recommendation tasks. In an untargeted setting, the objective was to degrade the overall performance of the model. In a targeted setting, an attacker specifically seeks to make changes in the network such as recommending an item to a user or not recommending an item to a user. Consider the example that I'm showing over here, where you have a temporally evolving sequence of graph snapshots, where each graph snapshot represents the interactions that users have with one another and users have with items on a particular day. Given this sequence of graph snapshots, let's say a recommendation model does not recommend explicit content to a kid. However, if there's an attacker that injects or poisons the training data by adding one edge at timestamp 1 and one edge at timestamp 2, then the prediction of the recommendation model can completely change, and the explicit content can be recommended to the kid. Thus, dynamic graph recommendation models can be vulnerable to such adversarial attacks and may lead to various different undesirable impact. So the goal of this particular work was to study how robust dynamic graph models are, specifically discrete time dynamic graph models are, to targeted adversarial attacks, where the goal of the attacker is not just to flip certain recommendations, but also do it without getting detected. Now we know that graphs evolve over time, and we know that these evolutions have patterns. So specifically, the contribution that we make in this particular work is that we create a adversarial attack that is constrained by what we call TAP constraints, which are time-aware perturbation constraints. Essentially, this creates a rule that the attackers are only able to inject noise, inject attacks into the training data by in such a way that the average rate of structural changes is preserved, as well as the rate at which the embeddings of nodes are changing are also preserved. So we created an effective attack method where projected gradient descent is used to find these effective attacks that satisfy these TAP constraints to flip the recommendations. We conducted extensive studies, extensive experiments, where we showed that the TAP constraint leads to a highest drop in performance in the specific targeted setting across 3 different dynamic graph models and on 4 different data sets for both link prediction as well as node classification tasks. Let me wrap up. Today, I presented 3 sets of work. First, I presented the dynamic graph model that we created to model continuous time dynamic networks. Next, I showed how we can model signed as well as dynamic networks. And finally, I presented 2 robustness use cases for recommendation tasks, where the first one was an untargeted setting and the second was on general discrete time dynamic graphs. I'd like to thank my students for their hard work and to the sponsors for supporting our work. I'd also like to thank the organizers of this workshop for inviting me to present, and I look forward to discussing with everyone at the workshop.